thanks a lot for coming. And today I'm going to talk about the first phenomenon we actually observed. It is at early like 2018, which is we call it frequency principle. And so yeah, so it's a kind of the whole purpose of this talk is to give you some sense that deep learning is no longer a black box. And at a later stage, I also have some questions or some problems. If you can really answer them without like just from all these understandings, you can answer these problems, and you will have a feeling that, okay, now I have predict certain aspects of this deep learning algorithm, particularly from these phenomena. You already have very rich idea about how that works. And first of all, still, let's go back to this my first lecture, that why we don't really have a nice framework that can help us understand the deep learning is because we may not really accumulate enough these pieces of this puzzle. Therefore, there's no hope that we really see these things as a whole. And therefore, for example, particularly at the time of 2018, we understand much less. Yeah, we collect pieces just like these ones, like we have a little bit hint about something underlying. However, there's no piece that really points towards how that thing exactly looks, or we don't really have these key pieces. However, throughout all these years, these 7 years of effort, and we uncover much more than we have at that time. And particularly, there are two of these pieces that are really, really important. The one is a frequency principle, as I will tell you about it this time. And the next one is a condensation. And I will give 3 lectures on condensation because it's so rich phenomenon that it not only shows it not only shows one piece, but tell us there's a lot of neighboring pieces you should uncover. And then, so there are lots of different pieces probably we can uncover, right? You see there are lots of theorems about this deep neural network, and each may contain some aspect of the properties of that problem. However, what kind of piece shall we kind of search for that could be more informative, right? And I don't know how many of you know this Edmund Husserl. Yeah, raise your hand. How many of you? I think it's a very famous German philosopher, yeah, and he opened up a new direction in philosophy that is called phenomenology, yeah. And so there's a famous quote that, oh, yeah, probably, yeah, that's true. You can see that it's really, it's a very famous German philosopher. So he said, natural objects, for example, must be experienced before any theorizing about them can occur. So he emphasized the fact that particularly that applies to the field of physics, right? We first observe the phenomena, and then this phenomenon guides us towards something deep underlying. And however, for example, from the time of Einstein, probably there's a different approach that, okay, you kind of theorize that, okay, there are something that should be equivalent, and then you derive the consequence. But for the very long time, we first observe lots of phenomena. So we have a strong feeling that there are kind of laws underlying all these phenomena we observe, and then we find ways or find some theoretical basis for that. And why I kind of particularly try to emphasize that, because there are lots of things you can do about deep learning because it's a so complicated system. You can try to analyze this system or look at this system from all kinds of different angles. Yeah, be it like from the mathematical viewpoint or optimal transport viewpoint or physics viewpoint or like even a psychology viewpoint. You can see all these different kind of viewpoints. And then each of them may give you a little bit of that thing. It's just like blind man to try to understand an elephant. However, I always said it's a danger to impose certain framework to that new object. And you kind of keep trying to move all these kind of things that is effective for certain problems. However, you kind of impose them to that new object. The Husserl suggests that, or actually he warns against this inversion of the process where we first have a theoretical framework, right? We start from some theory, and then we try to say, okay, probably it's this theory can help us understand this picture. However, so this inversion of the process, the theories actually can eclipse, misshape, or entirely ignore the vital qualities that encounters in direct perception. That's why I think for me, it's kind of easy to judge many theories are actually irrelevant in the sense that because I do lots of experiments, I observe lots of things. Initially, I don't really understand them, but I observe enough of them so that I have an instinct kind of intuition about what kind of theory really explains the things I could observe instead of I'm looking at going through all these proofs to say whether they are technically correct. Yeah, I'm not doing that. I'm trying to just directly perceive all these processes, these objects, and then I decide in which sense a theory could help me understand these things better. So that's a very important part of this very important idea to kind of uncover this. Particular about if there's any way we can directly perceive the whole process, for example, the deep learning, right? There's a learning process. If there's any way we can directly perceive the whole process, and then if there's some laws that should be underlying, we should have a direct intuition about that, and then we can theorize about that. And then the problem is how to experience deep learning. It's not a natural object, right? It's a kind of we can write down this mathematical formulation very clearly. For example, here's a kind of very standard supervised learning problem. You have some training data, and you have a hypothesis space where you have a nonlinearly parameterized function space, and then you're trying to find a function in the hypothesis space so that it interpolates all these training data. And you can see this process is no more than the following, where you have this neural network model, which give you a class of hypothesis functions. And then you run a gradient flow from certain initialization. It's not arbitrary initialization, but we often start with some specific initialization schemes, for example, LeQuin initialization, or He initialization, or Xavier initialization. Yeah, that gives us some initial point. We start from there, we run the gradient flow regarding this empirical loss function, and then we get, say, at infinite time, it converges to some theta. And what we really care about is this output function, which we use on testing data. And what we observe is that this function we learn at convergence often generalize well, even when the dimension of this hypothesis space or the number of parameters is much larger than these training samples. Okay, so why I list all these details here? Because there's no more in kind of minimal setup, right? Mystery of deep learning, and this framework is all the things you know, right? However, there's a mystery contains in this part, right? and then how to uncover the mystery, right? There's certainly something that is powerful, but you don't see that just from this formulation. As I've said, this formulation was there like at least date back to 1986. For 40 years, we know this formulation quite well, but nobody really finds the treasures that is hidden. Okay. And then now I tell you, okay, there's an important piece we should uncover, and what we do is first experience this. There are two key objects that is there. The first object is a trajectory in the function space, where you can see from some initial function which is not actually relevant to any training data. However, throughout this evolution in time, and gradually we know that it will fit all this training data well. And then it's not only on the training data, but also in the other points that we really wonder how the neural network learn from this training data, the information about these other points. And there's another thing, which is the trajectory in the parameter space, where in this space, where there's a gradient flow happened, and all these theta are kind of exhibit a high dimensional kind of trajectory. And then the common strategy, which exists there for actually very, very long time, is to choose proper statistics for observation. And why is that? Because they said it's a very high dimensional system, right? And then the only thing we can do is to choose some statistical quantities. For example, someone chooses a quantity like information or mutual information or things like that. They say, okay, this quantity is so important, then I should look at how these quantities evolves throughout the training, right? And actually, the first quantity we must look into is actually the empirical loss, right? Of course, the second one is kind of testing loss. You can observe how this testing loss evolves throughout the training. And then you say, okay, these two is kind of really plain, everyone observe them. And, but there's no more we can say. Let's observe something else, for example, the information. For example, the mutual information between the representation of neurons in that layer to the output, or the mutual information of that layer with the input. And we can borrow some ideas from information bottleneck theory to understand how this intermediate representation, right, the information contained in the intermediate layers evolves throughout the training. That is one try of this kind of choosing statistics for observation. Yeah, so what I can say is because we see that there's something that magic happens, right? The something magic is that it does not choose arbitrary theta that minimizes loss. Yeah, that is what we observe. But how to understand how it kind of chooses certain kind of global minimizer, in what kind of criteria it chooses a particular class of global minimizer and did not go to the other one, or do not have the tendency to go to the other. That's a magic part. So normally, yeah. Yeah, you're right. Right. That's right.
But it's probably...
You're right. Yeah, it's a degenerate, but in some local wells, in many directions, it's approximately convex locally. It will approach. So this, what we observe is that it's easy to make it approach a local minimizer. And particularly if this, you have a much larger model, you have a lot of parameters, actually you often observe is that you can get very low loss value. Yeah, almost zero loss value. Yeah, it means it's very close to a global minimizer. However, the fact is, in this scenario, when you have far more parameters than your samples, because each sample is like an equation, right? It's a constraint, but you have far more degrees of freedom to determine. So it's a kind of a EUPOS problem with infinite solutions. And actually, many of these solutions do not generalize well, because many of these solutions could be highly oscillatory in a sense, but later I will tell you.
So you say that in this...
Exactly.
Because you have...
Yes.
So then...
Right. Initialization play a role, but the picture is not like that. The picture is like there's a kind of a high-dimensional, these global minima forms a high-dimensional manifold. And yeah, they are connected. They are not, this picture, yeah, these are not the right picture. It's like this. And there's a certain direction where it goes here, right? Yeah. Yeah, the dimension of that manifold in this simple problem is m minus n. Exactly.
So you
yeah, and
basically there is...
right.
But they will be...
Yeah, and if that happens, the general situation is there are multiple isolated global mean. But as long as you make the network a little bit wider, and then all these global minima become connected, and there's the dimensionality of that becomes higher. And that's a general picture. Yeah, so the classical theory, yeah, there are these kind of possibilities, right? But here in some simplified setups, for example, we consider kind of analytic activation functions. And then there's no these kind of limiting cycles in this kind of system. They will converge to a certain point. But it's just there are too many of them. But yeah, it's related to that. And therefore, what you can see is that all these things have the empirical laws where we usually like, for example, RS, where S is a training data. And then this equals to 0 in this manifold. However, what we care about is the population one. Yeah, here it's L theta. This is a more kind of accurate thing where we kind of put this S here. So it's called, emphasize the fact that it is an empirical estimation of the population loss from the samples. Yeah, this is the empirical one. This is the empirical because you see only in training data are used. However, there's a population one.
I see. So there you...
Yeah, it's an integral over all possible x, all possible inputs. So it.
So then...
Stationary point, yeah. Yeah.
always get the same parameter.
With some common initialization. And that is something I have emphasized actually in my first lecture, is that the deep neural network actually are difficult to tune in the time of like 90s, where only very few people knows how to, for example, properly tune this hyperparameter, particularly regarding the initialization, how to properly initialize the network so that the network converge to some global minima, but also generalize well. So then later, at our time, we have lots of initialization schemes. We call Lequin initialization or He initialization, Zabia initialization. If you follow these initialization schemes, they tell you, okay, give me the width of that layer, I will tell you what kind of variance of these exactly.
And what is the bending?
No, and it's not likely it's a kind of lower dimensional stuff or that. Generally, it's like, for example, here there's a point. This point has like, it's a target point where it has 0 generalization error, right? And then in a neighborhood, right, everyone is like very good. Right, so it's not a lower dimensional stuff that make it good. It's just if you go into somewhere near this kind of a target, that
There is not a good...
there are. There are. In our recent work, I will talk in the later talk regarding the condensation part, the structure of the global minimizer, where this we call it like target set. How does this look like, and what's its geometry? And we will talk about that in the later lectures. Yeah, but here just we have some kind of relatively simple observation that, okay, these empirical laws in all these places are kind of have 0 empirical laws. However, many of them actually have very poor generalization or have very low testing error. But if we initialize with this, for example, this known initialization schemes, then what we get is actually very good. And why is that? Yeah, and if we start with some kind of common initialization scheme, in which sense this neural network avoids these bad parts and only focus on these good ones, right? And so regarding this kind of viewpoint, it's like, for example, there's an undergraduate student. You definitely know he wants to graduate from the college, right? but you constantly observe that there's a certain group of people, be it neural networks, that not only graduate. The graduate means the empirical loss is actually very low, right? The empirical loss is very low, then it graduates past some basic standard. But you constantly see there's a group of models called neural networks that not only pass this basic standard, but they are actually excellent in generalizing, right? And then you must say, okay, since it only based on this standard, it cannot explain their excellence, right? And then in which sense they become excellent? What are their motivations, right? In which path they kind of, or what they do to actually make them excellent, not only just pass the basic standard, right? And then what we do is to observe what you do every day, right? How these people do every day. You observe them, their behavior, and then you may have a guess, okay, in which sense or what they do to help to become excel. And that is the same thing we do. We try to observe the whole trajectory, the everything it has been done during the trajectory. And then we try to understand, is there anything they have done secretly so that make these things excel? Okay, the common strategy is that if you only observe some kind of very limited statistic, for example, what I observe is like how long you stay in your school, right? I can observe this quantity. And then, does it mean like if you stay here longer, you actually should excel, right? And whatever the quantity you choose for this high-dimensional system, then there's no guarantee that this quantity is actually very effective, right? Therefore, so we ask, is it possible to observe the whole trajectory without any bias? We don't say, okay, like a certain quantity should like actually reflect these kind of the essence of that, but we just try to observe the whole trajectory. So, but you also see the difficulty. The difficulty is that these things generally are very high-dimensional stuff. As long as this, for example, the trajectory is over 3-dimensional, you can't see the whole trajectory. Your eyes cannot do that. And also this ft, if this function is high-dimensional, you cannot perceive them as a whole. However,
You are asking whether
yeah, so the previously it's trying to have some projection, project at certain dimension. Okay, I have kind of strong confidence that certain kind of projection is actually very important in many systems. However, these kind of projection could give you more kind of bias than the actually effective. But let's look at the following, yeah. And here's what we do, yeah. What we do is we use a neural network. This is a tanh neural network with multiple layers. And these are the neurons in the hidden layers. And then we observe what they do to fit all these targets marked by this red line, right? And let's look at this again. And yeah. You observe everything, every details about the evolution in the function space without any bias. And you can see clearly there must be some patterns that is underlying. Multiple layer. Yeah, so this is like this four-layer tanh neural network. We just choose fully connected. It's the tanh activation function. Yeah, from some common initialization scheme. Yeah, because we normally, at that time, we kind of, there's someone believe that deeper is better. So if you kind of look at the things in the too shallow neural network, they said, okay, probably you are not telling us anything. So we just observe in relatively more common setup so that they may feel, okay, it's not about shallow, right? It's general. The same. All right. Yeah, you're right. And we actually tune lots of different parameters, and to ensure that this is not some pattern that is just particular to this problem or this kind of particular, for example, initialization or network. We do lots of, but I just show this cartoon here, but we did far more. Therefore, in this field, I always feel that it's sometimes very difficult to judge from these a few pictures that whether these phenomena are actually very general or not. It is from the person, if you know that the person usually did far more experiment than they show in this paper. And then that gives a lot of kind of credit to these kind of discoveries. And what we do is we did much more experiment, far more than what we show in this paper. You're right. Yeah, that's what we see in general. So yeah, from that you can see it first captures some core structures, right? And then refine these kind of high frequency or this discontinuous part. And then how to observe that more efficiently, since we have this basic understanding, okay, first later the fine structure. And then we know that Fourier transform is very efficient to help us, right?
So this is why.
Yeah.
And then because in particular,
I would say not exactly. There's later you will see there's a little bit difference because there are different frequency notions. In the frequency of the pictures, it's a little bit different from these things, but I will explain later. Yeah, but there's some difference. Okay, but since you know that Fourier analysis is kind of very effective, or kind of it's like a tool that help you makes these kind of behavior more prominent. Therefore, you observe everything, all the training process in Fourier space. Why it kind of. And what you can see is there are multiple peaks, and they gradually kind of fit more and more peaks. It's the same process. I just observe this process in the Fourier domain, and there's nothing more I've done, right? It's the same thing. It's the same thing as this cartoon. Oh, so this red is a Fourier transform of this red target. And this blue curve is a Fourier transform of this neural network output function. So therefore, that is you see, the theta is the same, but just put it in the Fourier domain with this. So this is initial, right? Initially, they are different. Yeah, gradually, yeah, more and more peaks are kind of captured. Right. That's right. That's right. So later, it fits all these training data perfectly. Yeah, and therefore, all these things match. But just the first peaks, or the first few peaks, are captured at much earlier time than the later peaks. It looks like that, but currently it's just an observation. You have that feeling, but at this stage, it's just observation. Yeah. Yeah, so why we emphasize the peaks here? Because the peaks are more stable than the rest. So if you really do the Fourier transform, actually there's a lot of tricky parts. For example, what are the interval? Because these are not exactly kind of periodic signals, right? What kind of window you choose actually matters. However, these peaks are more stable. So if you say you don't trust these kind of things, that between two peaks, artifacts of computation, not be reliable, but these peaks are actually reliable. Therefore, what we should focus is on where these peaks are captured. So actually, we have done all this kind of dirty kind of stuff to try to just compute it in a good way. Yeah, but you see, yeah, it's a very nice pattern you can observe. And later, we extract that pattern from this observation, says, okay, the DNNs often feed training data from low to high frequencies during the training, right? So you see, it's not a mathematical statement, right? But whenever you do this, you do what I told you, you can observe, you can have the same feeling, right? So that is, at that stage, it's an empirical observation, but it's really general. Okay, so it's and then from here, you may ask, is it because there's these peaks have higher amplitude? The neural network actually captures the Fourier coefficient with higher amplitude at the earlier time, right? You may ask this question, and then we kind of use this target where it has 3 frequency components at the equal amplitude, and then we try to see whether the neural network captures these different peaks at the time sequence or the kind of order of that. And here, the red means the relative arrow. And here, you can see when it's become dark red, the relative arrow is below like 10%. And then what you can observe, so this is the first peak that corresponds to lower frequency, and this is the second peak, the third peak. Yeah, they are of the equal amplitude. However, the relative arrow in this of the neural network output compared to this reference peak, like for example, the lower frequency peak like becomes dark red at a much earlier time, and then the second peak, and then the third peak. It tells you it is a frequency that really makes a difference or really determines when that peak was captured. So that is what we do in this kind of simple setups. Okay, then we observe something a little bit more fancy. It's a kind of, we try to ask neural network to fit a 2D image. So what we do, you see 2D image is a mapping from the coordinate of the pixels, like in the 2D, right, x, y, to the, for example, to some real value, right, to some pixel value. And then we ask the neural network to learn these 2D functions. And then we observe what is learned at first few epoch and what is learned at later stage. What you find like at like step 80, it learns some very coarse, this kind of things. And then at 2000, lots of details emerges, and at these kind of much later epochs, and they recover all these details, right? You can see that still it has difficulty in like capturing more details in this part, which correspond to much higher frequency part, like some sharp edges of that. If you really want the neural network to capture that, you may need much, much more training steps. And yeah, and that is what you can observe to use neural network for fitting. And then you have some confidence that the frequency principle is actually very general for this lower dimensional fitting problem, right? Because we observe everything clearly with our eyes, that there's this pattern there. However, in the high dimensional space, yeah, so all these neural networks are dealing with very, very high frequency data. For example, even the even the handwriting digits, MNIST, it's 784 dimensional. And if you consider these like CFA 10, it's easily thousands of dimensions. And therefore, whether this frequency principle still holds if neural networks are used to fit very, very high dimensional data, right? And that's a problem. And the challenge is that if just feed this one-dimensional data, we can observe the whole process by our eyes, right? We can have a sense. However, it's not possible with this very high-dimensional data. Therefore, it means now we need to use some statistics to tell us whether this high-frequency part, whether high-frequency part or lower-frequency part are learned. And then, first of all, I need to tell you there are different notions of frequency. And the first frequency is the image frequency. But actually, it's not that relevant to the frequency we use when we use neural network for these image classification problems. The imaging frequency, and then, for example, it's a constant red, then that means zero frequency in that space. And then, if there are sharp edges, for example, there are trees and sharp edges, that correspond to the high imaging frequency. So the image, in terms of imaging, so these Fourier transforms are kind of two-dimensional Fourier transforms. However, here, what we care about is the neural network output function. And the neural network output function, even for MNIST, is like 784 dimensional. So the frequency principle we observed at the earlier time is a frequency regarding this very, very high dimensional mapping, right? Therefore, I think none of you have even ever tried this kind of Fourier transform in higher than three-dimensional functions, right? You've never done that. Therefore, if you did not really observe this frequency principle with these lower dimensional functions, it's impossible for you to even think about Fourier transform with this kind of function, right? It's kind of forbidden. But since we have clear indication in the lower dimensional cases, now we know we must overcome this difficulty, okay? And then, so the idea is, first, the notion of the frequency here, we call response frequency. That means if there's a certain, the high frequency corresponds to the following situation, where if we perturb, for example, this input, this X, a little bit, and there's a huge change in its output, and then that corresponds to the high frequency, high response frequency. And low response frequency means, okay, I perturb X maybe a lot, but still the output does not change much, right? So then it means that this kind of function is relatively, has a low response frequency. So that is how we understand these things. And in that sense, these adversarial examples tells you, okay, in these kind of functions we learned, there are certainly very high frequency components in these kind of response functions. Okay.
So we can
Yeah.
discuss this, I think.
You're right. So first, here, what I want to say is that this kind of, whenever you have a perturbation or unseen to our eyes, a perturbation unseen to our eye, that means it's very small perturbation. And then the output change a lot. Then that is high frequency for that response function. That's right. Yeah, but here, that's why that happens. Actually, in these kind of special directions, you don't have data constraints because these natural images, we have a basic understanding that they lie in a lower dimensional manifold. Therefore, you don't have constraints in these lots of these orthogonal directions. And therefore, so in these directions, it could be there are some high frequency kind of things that happen because you have no constraint on that.
So somehow
Yeah. So let me give a very simple example that can illustrate some point. For example, we have a classification problem that we try to classify these two classes. And then, according to frequency principle, what kind of a decision boundary the neural network prefers to learn? Do you know? Exactly. That's true. And you can see in the Fourier space, there's a reason that this is simpler. But there are certainly some, around this, you can see a tiny perturbations gives you another category, right? And here it's also true. It's very close. There are some of these kind of samples that are very close to the decision boundary that leads to some sharp changes in the category. And how to make it more robust? Actually, it suggests a different kind of this boundary is a bit more complicated. However, it is more robust to these adversarial attacks. So therefore, this is a deeper part in that story. It says, okay, we tell you there's a frequency principle which which neural network prefers to learn low frequency fitting. However, why there's this kind of high frequency happen means you perturb a little bit, there's a drastic change in its category. I tell you, okay, so this frequency principle tells, okay, to find some simple kind of decision boundaries, and that makes it kind of lower frequency. However, these simple boundaries sometimes are, there could be a lot of these kind of samples that are very close to the boundary, but due to the simplicity, you tend to learn this vertical line. But if we increase the complexity, and then these higher complexity boundaries are actually more robust. Right. Or what you do is to do adversarial training. Adversarial training says, okay, essentially just get a lot of perturbed samples, right? These perturbed samples kind of, you not only have these clean samples, but also have all these perturbed samples, and you give them the category, right? As long as you have all these perturbed and give them these kind of category, and then you force the neural network to learn more complicated boundaries. So that's, there's a kind of, this is a kind of new understanding that why the neural networks are not very robust to adversarial attack. It is because of simplicity bias. It is because of frequency principle that asks, so without additional information, I always learn this kind of simpler kind of decision boundary. However, sometimes simpler decision boundary can be not so robust. So that is a strategy to kind of force a network to be a little bit more robust. However, so still, that's not the best strategy for robustness. Okay. So that's just a general comment. Yeah, so why I'm not recommending that? That is because, so it's like I assume the kind of distortions are like Gaussians around these training samples. But the actual perturbations we care about, for example, the natural image we care about when there's a snow, right? And then this perturbation is not this kind of Gaussian perturbation. And it's also not so tiny. But still, we want the network to be robust to these kind of distortions. And therefore, so this framework says whenever I understand the perturbation, for example, it's Gaussian perturbation, and then I just use this framework. I just add them, and then the neural network deals them well. However, the real situation is that this is not the real distortions we want. We want something more kind of profound kind of distortions. Therefore, it goes, so the better strategy is that we have some better architectures that prioritize the better decision boundary or more robust. So that is more kind of intrinsic kind of strategy, but these are just says whatever you have some assumption, I have a strategy. All the architectures, yeah, it's a like so. So all this architecture has this kind of implicit bias. However, I want to say that what does simple mean is different for different architectures. For example, the convolutional architecture with local connection, what simple means is different from what simple means for this fully connected network. So there's a kind of things we must be careful. So this kind of framework does not tell that details, but the later condensation part will tell you all these details, what the simple means for different architecture. But here it's a kind of the coarse-grained perspective to that. Okay, and now let's try to understand this frequency principle or examining frequency principle for high-dimensional real problems. So what we need to do is this or non-uniform discrete Fourier transform. So why this is necessary? Because for like imaging data, what we all have is like, for example, 60,000 training data, right? And these are the data points, all the data points we have for this Fourier transform. So therefore, a natural choice is to use this we call non-uniform discrete Fourier transform, because there's no guarantee all these 60,000 kind of training data are on the grids, right? Usually we kind of use the data in grids. Therefore, it's called non-uniform discrete Fourier transform, just to use this information. So, but this kind of the formulation is really simple. So we can do the Fourier transform on these non-uniform training samples. And then still, there's a curse of dimensionality in the sense that all possible combination of the frequencies, because now the frequency vector is a very high dimensional vector. So the number of all the possible frequencies grows exponentially with the dimension of the problem D. Therefore, it's impossible to examine the frequency principle on all these possible frequencies in the high dimensional problem. And then we have like two approaches, like choose proper kind of ways to coarse grain that problem. So the one way is a projection. So we choose a very special direction, K, so along certain kind of P, for example, the principal component of all these training data, right? Kind of project the problem on that P1, and then we consider the Fourier transform just along these, the direction of the principal component. And then I got a 1D Fourier transform, and I can do the same thing. That is regarding the projection. And another approach is the filtering. I kind of use some filters to the data so that I kind of separate data into the lower frequency part and the higher frequency part. I say, okay, which part converges at the earlier time? There are two approaches. Okay, and then now let's see these. We use this, for example, projection approach on these two real training data, MNIST and CFA10. And now, as long as we have a direction for projection, then that becomes a one-dimensional Fourier transform. And then we can do the same. We can compute the one-dimensional Fourier transform and obtain all these kind of peaks. And then we look at their relative error and see when the relative error becomes sufficiently low. And what we can observe is that, so from lower frequency to higher frequency, right, there's a delay in the time when the relative error becomes sufficiently low. And we can also do it on CFA10. We can choose these kind of black dots as these reference points. And still, when you look at the relative error, you can see the lower frequency one like are more quickly converge to a sufficiently or obtain a sufficiently low relative error, and the high frequency ones are kind of has sufficient delay. So you can also choose different projection direction, and then you can observe these similar patterns. And that is what we do in the high frequency. It's not possible to observe which is faster, which is kind of slower regarding all possible frequencies. However, we can always do this kind of projection, have this kind of partial understanding. And there's another method that is called filtering method. The filtering method says, okay, what if in the Fourier space we kind of decompose this target into two parts? One part is a lower frequency part, and the other part is higher frequency part. We kind of try to decompose this target in Fourier space into two parts. And the kind of naive choice is this truncation, right? We just truncate the target in the Fourier space, only remain this lower frequency part. However, this kind of truncation is very difficult to realize. So what we do, we use this Gaussian kind of thing to mimic or to soft truncate the and then we got a lower frequency part and a higher frequency part. And then what's also good is that this kind of truncation, you use this Gaussian function in this original domain, it corresponds to a convolution with Gaussian. And it's just like a filtering. You got the lower frequency part. And also the difference is the higher frequency part. And then what can you observe is the following. You can choose different delta. What is delta? So delta is this kind of truncation frequency. You can truncate at different ways to separate the lower frequency from the higher one. So we can, for different network, you can truncate at the different kind of frequencies. And then, but consistently, you can see that this lower frequency part converges faster than this higher frequency part. And that is we do for these higher dimensional real problems. Okay, and now you can see it's, that's what we have. And I think I can rest here for a while, and later we come back. Shall we start? Okay, and now you have a better idea, particularly regarding this lower dimensional problems. You have some idea about the frequency principle. And now let's talk about implication. So if we know it, what we can kind of understand. First of all, let's think about the problem with generalization, because previously what I show you is that for the target I have sufficient samples, right? So all the neural network to do is to approximate well this kind of target because I have kind of sufficient samples. But we know that neural networks are especially good for generalization, right? To fill the missing spaces. And then here's a problem where we have a original this kind of image of a cat, yeah, and still we kind of regard this image as a 2D mapping from the location of the pixels, x, y, to its pixel value. And then we try to use this neural network to train on this training data, which is visible to you, right? This kind of training data. And then, of course, yeah, we know that the neural network, the function, will give you a function in this whole space, right? Because it's continuous, right? It gives you the mapping in the whole space. And at the initial stage, still there's a frequency. It captures some core structures of this cat. And then in this kind of, in a kind of middle stage, there are a lot of details has already emerged, but not to that kind of detail. And at a much later stage, actually it's a kind of, yeah, it's a kind of a million epochs. So you see how we do things. We, at earlier stage, whenever we talk about something, whether it converges or not, many times we go to a million epochs or even more to make sure that it's actually converged to some places. But I often observe someone claim convergence or claim unable to convergence just using like several hundred steps, right? And then that's not a good thing. And sometimes a neural network can need much longer time. So, but you can see that it fits the kind of missing pieces quite well, right? And why is that? Why it is able to, based on this kind of existing pieces, able to fill in the gaps? You can see frequency principle definitely help you expect this kind of fitting results. Okay, so that is about this kind of 2D image restoration, and we can use neural networks to do that. Just based on the frequency principle, you expect this kind of a reasonable. And then there's a generalization puzzle. So the generalization puzzle says, okay, the neural network, why a neural network, like over-parameterized neural network, can actually generalize well, right? And now the frequency principle suggests that the deep neural networks actually prefers lower frequencies, okay? It means that whenever you see that neural networks learns well on some problems, for example, these imaging data, and then because we know that the neural network prefers lower frequencies, then we ask, or we have some understanding that it must be because the underlying target, right? The underlying target has some lower frequency structure, and then we can examine whether it is indeed true on this, for example, CFA10. What we do is actually using some projection. We project all these kind of CFA10 data, which is over 1,000 dimensions, along its principal component direction. And then we do the Fourier transform. We can see there's a nice decay in its frequency domain. That means these imaging data are kind of dominated by lower frequencies in terms of this kind of input-output mapping, high-dimensional input-output mapping. And therefore, so just to capture, because the lower frequency dominates the target, therefore the neural network, just based on kind of limited data, is able to well capture these lower frequencies. But the high frequencies, there could be like a little more difference. And since we know that there's a no free lunch, right? No free lunch, so the frequency principle is good for lower frequencies, but of course, the higher, if the problem has higher frequencies, that means that deep neural networks actually suffers. Actually, there's a kind of earlier result which proves that in certain particular class of functions, the neural network cannot generalize. There are such results. There's a famous kind of example, or this kind of data or target is called parity function. What is parity function? So there's a high dimensional input x, which are discrete, only takes a value of -1 and +1. And then this target is to make the product of all these dimensions of input. So in which sense this one is a kind of high frequency? You can see whenever you flip the sign of one dimension, the output will change its sign. So it means that whatever there's a tiny perturbation to one dimension, then the output will totally flip. And that is kind of really high frequency. Therefore, for this kind of function, you only let the neural network see part of this training data. And then, so first of all, this black line is a Fourier transform along the one principal component, and you can see it's really dominated by the high frequencies. However, if you only have limited samples on that, what neural network learns, that's the Fourier transform of what the neural network learns, right? And it's kind of has significant lower dimensional part, lower frequency part. That is because the neural network prefers to use this lower frequency kind of feeding. Therefore, if I just go back to the earlier kind of problem, where we have this exclusive OR, what is said is that, for example, so this is a kind of 1, 0, 1, and you know all these three kind of, the categories for all these three, how do you predict the rest one? And now, based on frequency principle, what is your prediction? What neural network will predict on this part? Actually, definitely plus. Why is that? Because this is a lower frequency in the sense that there's this kind of neighboring kind of thing. It won't be consistent with the neighboring. Therefore, just based on this understanding, you have to say, okay, although I have a neural network with universal approximation power, that means even though there's a kind of, this is a different category, the neural network is still able to approximate that well. However, the intrinsic tendency is that it tries to kind of use this lower frequency interpolation. In that sense, before trying all these kind of things, you already have this kind of expectation. And, in that sense, it's not really a black box to these problems. Okay, and then, so since the output of the neural network totally misses kind of key high frequencies, therefore, the testing accuracy is just 50%. It's a random guess. It does not learn any pattern in these kind of problems. You mean this one or this? Oh, in the drawing there.
This manifold.
Yeah. Yeah. Right.
So this low.
Right. That's exactly true. So this lower frequency part is the region where it concentrates at, and this higher frequency part, there exists a certain initialization that converge to them. However, so later you will see there's special requirement for this initialization to indeed converge to these parts. And later we have understandings on that part too. How to overfit, use the neural network to overfit the data.
So you could.
Yeah. You are right.
Okay.
You can coin up because as long as there exists a minimizer there, the neighboring will converge to that. Yeah.
Somehow.
Yeah, from some common, we call common initialization. Yeah, it means that you adopt the, for example, the co-initialization or this kind of initializing strategy. That is what I mean by common. Actually, no. So it's very, very difficult to establish this kind of probability result in a sense that you see, if you don't really understand this manifold, how can you possibly have this kind of correct understanding of this kind of probability? Therefore, these kind of things are the best we can expect at this stage. And the later stage, if we really want the right kind of sense of probability, we must review all this detailed structure of what is good and all the details of the loss landscape. That's essential. Okay, and then a very, very important kind of aspect of the frequency principle is that it tells you what you should expect when you early stop the training. Actually, early stopping is quite often used tricks in the neural network. I don't know how many of you have tried early stopping or have you ever used early stopping? Yeah, it's actually kind of very standard. But the problem is when you early stop, definitely there's a criteria that tells you, okay, you have some validation set. Whenever the arrow on the validation set starts to go up, then you should stop there, right? But why or what happened when you actually stop there, right? And the frequency principle tells you, okay, if you naturally allow this training to go down the loss, then it will capture more and more high frequencies. In some problems, these high frequencies are very clear. For example, in these kind of problems, this noisy kind of observation of this underlying, for example, this sigmoid curve, this noise contributes to the high frequencies because we know white noise has lots of high frequencies. And then if you, for example, you kind of using some validation or some testing set, so you will see that you can stop at this green line because this testing data the accuracy starts to be worse or loss starts to go up. But if you observe what happened here is that this blue curve is what you observe when you stop. It only captures the lower frequency part of that data, but did not fit all these high frequency noise. And in that sense, it tells you why early stopping is actually, for many times, are very effective in the deep neural networks. Because whenever your problems have noise, then early stopping helps the neural network avoid feeding all these high frequency noise. And many times it's a very, very kind of effective. Right, yeah, multi-grade, yeah. Actually, no. So you can do this. However, so what you can find is that just use a big enough neural network to let itself train on the data adaptively. That's the best strategy. Whatever you do based on your understanding is not as good as the neural network itself.
So you can
Yeah, it's a, yeah.
method that is
So it's not that you cannot save computational resources. It's just that in terms of generalization, it's not as good. It's generally not as good. Yeah. So, but particularly, for example, in current large language models, people do want to save computation. For example, you start training a kind of 7 billion parameter model, and then you want to reuse it as give some initialization for the kind of 14 billion parameter model. However, the practice is that if you have enough resource to directly train a 14 billion parameter model, you just directly do that. Yeah, so you can save computation, but in terms of performance, directly training a large model is always better. And here, from this kind of understanding, you can see there are reasons why the neural network itself is adaptive enough, right, to help you avoid this kind of, for example, the overfitting or these kind of things. Itself is just so powerful. We just try to review in which aspect it is so powerful that lots of things are done automatically. Okay, so then we have this answer to the problem. Actually, it's proposed by Liu Breeman, that is told when should one stop the backpropagation and use current parameters. And now you have a very good understanding. Okay, So there's a certain problem, there are certain high frequency we don't want the model to capture. Then we just stop the model there. And then goes to the last part, it's about the theory of frequency principle. Yeah, and first of all, there's a kind of really kind of a coarse kind of analysis of that process. So first of all, if we have this neural network that represent a one-dimensional function, and then we can do the Fourier transform. So the key for the Fourier transform is to consider this sigma. For example, here we choose this tanh function because it's an analytic function, and then we know it's an expression of the Fourier transform. And what you can observe here is that here k is the frequency. And as k goes larger, there's an exponential decay term in the Fourier transform of this h hat. So that tells you, okay, whenever you have a very smooth or analytic activation function, then you got this exponential decay in the Fourier transform. And then now what you do is to rewrite the loss function as a frequency domain. And then since you have this Parseval's theorem, you know that it's a kind of equivalent to the original L2 loss. And of course, in this L2 loss, in this frequency space, you can see there's no priority over the lower frequencies. All the frequencies are regarded as equal in this L2 loss. However, you see when you do this kind we call backpropagation, right? Or when you take the gradient of this, for example, the loss at certain frequency regarding the theta. And then what happens is that, so you have like several terms. Particularly important term is this exponentially decay terms in the frequency domain. This comes from the smoothness of the tanh activation. So you can see this exponential, initially in this LK, so this, because there's an L2 norm, so all of these L are kind of given the same priority. However, as long as you take derivative regarding the theta, there's an additional decay term in the frequency domain. That tells you, okay, so if you think about the directions of perturbation on the gradient, this gradient direction, then most of these energies are concentrated on the lower frequency part and less on the higher frequency part because of these exponential decay terms. That is here that tells you about the energy of the loss term, the evolution of that loss. Okay, so that's the basic reason why the lower frequency kind of thing always dominate over the perturbation over the gradient direction. So it is the smoothness from the activation function. Okay, so the key insight is that the smoothness or regularity of the activation function can be converted into the frequency principle through this gradient-based training. Yes, ReLU, if you do the Fourier transform, you can see, of course, it's in the sense of kind of distribution, right? You do the Fourier transform, and then it's a kind of 1 over k squared. Yeah, and then that's a decay, 1 over k squared. If it is a Heaviside function, then it's 1 over k, right? If it's, yeah, it's like a ReLU square, then it's like 1 over k to the third. So that means like if you increase the smoothness of that activation function, you get a faster decay. That means the higher frequency has lower priorities during the training. That's, so in many numerical problems, so they do use like ReLU square or ReLU third. In somehow, what they try to do is to further prioritize the lower frequencies. That's what they can do with this or ReLU to the third. I would say, so later there's a result that says, okay, it's better to match the regularity of the problem. So for example, your problem, the decay is kind of 1 over k squared, then ReLU is pretty good. it try to match the decay of the activation with the decay or regularity of the problem itself. That's the best way. You adopt. All right. That is a suggestion. Yeah. Later there's a result that suggests that, but it's a kind of bound, but it's not 100% true. But for some PDEs, probably we have a little bit of understanding, but not necessarily the. So I would say for many data, they are not that, they don't really care about this regularity, because regularity is really local stuff, you see, right? It's a tiny bit of things can change the regularity significantly. But in many problems, for example, image recognition problems, we don't care about this tiny stuff. If you miss a tiny stuff, we say, okay, it's perfectly fine. Therefore, this kind of very kind of sophisticated notion of this regularity does not really apply to this, for example, imaging problems. Right? We don't think it's an intrinsic kind of thing regarding these kind of training data or this kind of, for example, language data, because it's kind of discrete in nature. Not necessary, we really think. Also, in these problems, we often use very smooth activation functions. Yeah, it's a kind of, but ReLU does not say ReLU is not good. Probably because there's just, we don't really care about that much high frequencies. It's a, really care. And then these different things in a finite range of this frequency domain, right? They are kind of equivalent in a sense. Yeah. So, and that's the understand. But for PD, it's probably more intrinsic. Yeah. And then, so if we try to understand it better, so there's we can analyze this frequency principle in this kind of neurotangent kernel regime, where always says that in certain kind of setups, for example, when the neurons goes to the number of neurons goes to infinity, and then so the whole dynamics. First of all, you can write down the dynamics in this function space. So initially, what you have is the dynamics in the theta space, right? It's a gradient flow in the theta space. However, you can rewrite that equation in the function space, because frequency principle is about the rules in the function space. And when you write down, you see that there's a kind of a kernel terms here, and there's this kind of arrow term. This function actually looks like a differential integral equation, in the sense that in this kernel part, there's an integral over this data, right? There's an integral, but here's a differentiation. So this integral part, this kernel part, actually modified this priority of these different arrow terms. And then what we can see is that these kernel terms in the neurotangent kernel regime, in a very special regime, where it's almost the same as the kernel function at the initial point. Therefore, all you need to do is to estimate this kernel function at the initialization, which is just theta generated from this Gaussian random distribution. And then, so this neurotangent kernel theorem tells you, okay, so we can do that at certain kind of limit. I won't detail about that. I will detail that in a later time. So as long, yeah, okay. kernel perspective. Yeah, so first of all, what we can do is as the following. We have a dynamics in the theta space, and we want to write down a dynamics in the function space. And what we do is just directly, so for example, we have this kind of partial derivative regarding t, right? But this is induced by this equation. The later equation is induced by this equation. Theta, the kind of thing in the theta space. So what's the connection? So probably let me write down a few kind. Yeah, exactly. It's like that. It's changing the metric in the gradient descent. So therefore, this kind of kernel part gives us a different kind of priority over the space. And if you take derivative, and then we realize that everything of this dynamics or this partial derivative actually comes from this theta. We care about the evolution of this hx, but what we have is this dynamics over the theta. Therefore, you write down.
H is
the neural network. Yeah, exactly. And then you can see that it's over theta x. And then there's a transpose over theta dot. Something like some dynamics kind of that looks in this way. So what are these? These are partial derivatives of this neural network regarding each dimension of this theta. This gives you a bunch of tangent functions. And these tangent functions, they are evolved. So they are kind of changes at different theta. But the evolution of theta is at this term is a theta dot. So what theta dot? It's just a chain rule, exactly. And this one, we have a dynamics, which is written up, on the up. And therefore, these terms, yeah, it's a L theta. Yeah, and there's a minus in front. And now let's further write down. And that's talk about this term. It's a L2 kind of a loss term, but we need to kind of operate on the chain rule regarding the inner H. Yeah, and there's a further this kind of H theta. And also there's these arrow terms, these yi. Yeah, and there's a summation. So here there's a xi. You see, there's a xi. In this side, there's a xi. Therefore, there's a summation. We can write the summation outside, and that is a general way. I equals to 1 to n. So that is what we get here. And what we do is to consider this part. Look at this part. So whenever you have some theta, right, there's a kind of, so the kernel function looks like, for example, k x prime, right? This is a kernel function, looks like that. And now what you do is there's an inner product regarding the dimension of theta, regarding all these tangent functions, and then you there's a summation over all of this. And then you got this one variable x here, which is x regarding this h. And there's a xi, which is a sample direction, right? And then the sample direction will be combined with all these arrows. And then, so that is how you derive these kind of equations, which is written down in red. And written down in red, but what you need to be careful is that this theta, there's a t here. There's a t here. So these depend on t, means the kernel generally evolves throughout the training. However, NTK, neural tangent kernel, is a very special regime where we know that there's a lazy training behavior, means that in some limit, we know that this theta infinity is approximately, theta infinity is approximately theta 0. Yeah. It just means that compared to the magnitude of theta 0, the difference is a kind of, can be ignored in certain sense. Yeah. Actually, not true. So this is a not good way to write down this kind of thing. A better way is to write down this k theta infinity, because the kernel depends on theta. And then x prime. So all we care about is that whether this kernel, so this one can be there's a little bit difference compared to theta 0, because otherwise it does not learn the training data. But all that happens is that there's just a tiny bit of change regarding to theta 0. That is enough to feed all the training data. And all that left is that these kernels are almost the same, means that if you look at their spectrums, they are very close to one another. So, generally, no. Generally, no. However, this is a setup where everything becomes linearized. Therefore, we can see clearly which modes are learned first. Otherwise, there's a kind of correlation between all different things, and we cannot kind of quantitatively analyze this system. So I must say, this theoretical framework is very, very limited. However, if we can extract information from that kind of special analysis, then this information could be really help us. Yeah, and that is what we do. So we are not saying that this, actually the frequency principle holds no matter it is a neural tangent kernel regime or there's an evolution during that. It's not. Like the first analysis tell you, okay, all that says is that there's a kind of decay terms that is informed. That is independent of this location of theta. But the kernel will change. However, the easier model to analyze the frequency principle quantitatively is to consider the neural tangent kernel regime. So we try to do some analytic analysis so that we can understand the effect of the frequency principle better. Okay, so that's something about the neural tangent, the kernel dynamics. And what you can notice is that this kernel dynamics is a linear dynamics. This is a linear. Okay, once you fix this theta, right? You fix this theta to theta 0. So this kernel becomes fixed. And then the whole dynamics is just a linear dynamics. Okay, so, and then there are ways to do a little bit like problem simplification, because otherwise we see the frequency principle, we can never quantitatively understand the frequency principle. And that's the situation we encounter. So we kind of simplify this kind of complicated data to this 1D problem. And then we simplify this multi-layer stuff to a 2-layer kind of ReLU neural network with a particular form that is to facilitate our analytic understanding. And there's a kernel gradient flow. We assume that we are at a very special called neural tangent kernel regime. And then under this situation, we can analyze the frequency principle analytically. I will skip some of these details because doing these Fourier transforms, particularly in a high-dimensional space regarding these activation functions, we should be careful. It's in the sense of distribution. Yeah. And there are some thing you need to be a little bit more careful. But probably just to give you a little bit sense about this part. So this is a general form of a neural network activation function. We have a kind of single variable function g, and then what we care is that it's a multivariable function in X, but it's a projection over a certain direction of nu. And then if you do the high-dimensional Fourier transform regarding X, what you can expect is these two terms. This term is simple. It's still this kind of the Fourier transform regarding this one variable function. It's a 1D Fourier transform. However, this term is kind of a restriction. It tells you, okay, since this G function is a constant on the direction orthogonal to nu, right? It's this G is a constant on all these directions. Therefore, if you do the Fourier transform, you only get a line in its Fourier. The direction of this line is along this nu direction. And so for all the other things in the Fourier domain, you don't see anything. So that is because if you do the Fourier transform of delta function, for example, you're confined over a certain direction. And then the Fourier transform becomes a constant, right? And if you are careful enough, then you can derive these kind of relations that will tell you how to do this high-dimensional Fourier transform. And then let's look at the result. So here we analyze a two-layer ReLU network. In the neurotangent kernel regime, we also assume sufficiently wide distribution of this L factor that also facilitates the computation. And then we get the following, we call linear frequency principal dynamics. Let's look at these dynamics. First, where does this Casey square and the Casey to the fourth come from? So this comes from the Fourier transform of these tangent functions. For example, the tangent functions of this Wi is this ReLU Ri, right, this later term. And this ReLU function in the Fourier space, it has decay of 1 over Casey square. And then because this kernel function, there's a two-part, right? One part Casey square, and the other is also 1 over Casey square. So it contributes to 1 over Casey to the fourth. It contributes to this term. And where does this first term come from? It comes from when we take derivative regarding, for example, this Ri. And then this ReLU becomes Heaviside, right? If you take a derivative of the ReLU, you got Heaviside. So Heaviside, the decay is 1 over Casey. Therefore, 2 1 over Casey leads you to this 1 over Casey square. So that is where these terms come from. And then the relative strength of these two terms depend on this initialization. These R, W are the, you see, are the R and W's at the initial. And then this is a kind of expectation at the initial because it's randomly sampled. So depending on the balance between these two, the one term can dominate over another. So that is the dynamics we write down. So this is a kind of really nice equation in the sense that you can see in the Fourier domain, you can see a very clear kind of a priority, right? And for example, the lower frequencies, particularly around 0, are highly prioritized. And the higher frequency, there's a decay of priority of learning throughout this process, okay? And what's special about this? Remember that all these dynamics, the goal is to use this model not only not only fit this training data, but also to predict the rest of this data. Therefore, you can see that what we can see is that generally, for example, we are learning this very high frequency curve, but we only have relatively kind of sparse sampling of that curve. And we use this linear frequency principal dynamics to learn that. What you should expect is that you learn this lower frequency curve, right? And you did not really learn these high frequency ones. So the reason is that these dynamics prioritize over the lower frequency learning. If lower frequency part is sufficient to explain everything, then you just stop there, okay? So that is what happened. But if you have more and more data, this dynamics tell you, okay, so finally all the error will go to 0. Just lower frequency converges faster because the exponent in the exponential is determined by this coefficient. Therefore, so you can have very clean sense of frequency principle in this linear frequency principle dynamics. Okay. So, and then now let's further look at this. So there are ways to connect this gradient flow training with a static optimization problem. So this static optimization says that what we minimize is this particular kind of integral. That is an integral over the frequency space. And then there's this pre-terms that is the inverse of this, this coefficient in the linear frequency principle dynamics. But there's an inverse. Therefore, you can see this form serves as a penalty, right? It's regarding the fitting. It says that, okay, the HXI will fit the YI at convergence, but I have a penalty. This penalty is the inverse. There's an inverse term. That means I give higher and higher penalty over the high frequencies, right? And then I choose among all the fittings the one with the lowest energy regarding this function, right? And that static problem tells you how this linear frequency principle dynamics choose among all these possible global minimizers. So that is regarding this, this special energy function. Okay. And there's a little bit more that we can make connections to the splines, to the interpolation problem. And if the dominant term is this Casset to the -2, and then this minimization problem written to the real domain is actually minimizing this, derivative, the energy of the derivative, and then it gives you a linear spline interpolation. However, if the dominant term is a Casset to the -4, and then that gives you a minimization of the second order derivative, that gives you a cubic spline to this interpolation problem. And then experimentally, that is what we observe, is that when we set proper initialization, so to that one terms dominate another, for example, the Casset squared terms dominate, and then the expectation is that, so it learns a linear spline. It linearly connects all the points. And in the other case, so it's a Casset to the 4th, and then it gives you a more smooth interpolation, which is a cubic spline. So, and I think I will end up here for today, and I will quickly cover that in the next lecture.